Hey, we've got a bit of a special one on the bench today. We've got a Tektronix 2467B 400 MHz 4-channel analog scope. This is a bit of a beast of a unit. The 2400 series is generally considered some of the best analog scopes that Tektronix ever made. Possibly even the best scopes ever made, period. Generally up there with the best, anyway. But this one is the, like I said, the 2467, which makes it a little bit special. This is the top of the line, the top model. The 2465B is one that you may often see around, like people looking for them, because that's a 400 megahertz 4-channel, just a general purpose scope. 2466 is something that you'll find probably most commonly in Japan. It's got a smaller CRT that's run at a higher voltage and basically a slightly overclocked CRT to make it real bright, which makes it good for photography. But the 2467 has one special feature that all of the others lack, and that's sitting right here. This CRT is a little bit special. It's got a system in there that actually amplifies the electron beam so that you can see very quick traces a lot easier. If you imagine you've got a very fast trace, you're trying to see a very small, like a very quick signal. What happens is that trace is going across so fast that the phosphors can't react fast enough. The electrons aren't hitting the phosphors in any particular position long enough to make a bright trace. So that's where you get that old stereotype of the engineer sitting in the darkened room squinting at the little CRTs and stuff, because if they're looking at a fast trace, it's just really, really dim. To counteract that, they designed this CRT, the MCP, micro channel plate, and it's almost like those horizontal blinds, like the Venetian blinds or something, where it's like angled pieces in a grill, like strips going across, and that's very, very small inside, like very fine pitch inside. And if you imagine you've got the electron beam that comes from the back of the gun, travelling towards the front, hits the phosphor and makes a dot on the screen, or a line if it's travelling in any particular direction. And what happens is there's this louver that's in between. So rather than the electron beam striking the phosphors directly, it hits this louver kind of array, and hits one of the louvers, bounces off, taking a few more electrons because that louver is charged, and it bounces back and forth. Each time it hits the louver, it will take more electrons. It's bouncing back and forth, creating basically an avalanche of electrons until it reaches the other side and sprays out all over the phosphors, and makes a much brighter trace. So that way you can have a very fast trace and still have it bright enough to see, without having to sit there and squinting in the dark. Now the trade-off, of course, is that if you're pumping so many electrons at the phosphors, you do run the risk of burning the screen out. You've got to make sure that whenever you're using one of these MCP screens or CRTs, you always turn the intensity down as low as you can bear. If you run it too bright, you'll very quickly burn that CRT, and they're not very common. They're only used in the 2467s, I believe, and also there was a scope maybe in the 7000 series. I can't exactly remember, but yeah, they're not that common. There's not like a general purpose scope where you can find CRTs all over the place. So you've got to be wary of that and be careful. Try to minimize using these sort of scopes for everyday general purpose use. Just use them for the times that you need them. So I've actually got two of these things sitting here. I've got the 2467B and I've got the 2467. These are the two models that were released. They're not really made to stack, so I just hope it doesn't fall off. The 2467 is a 350 megahertz. I only made the two models. There was no 2467A or 2467C. It's only 2467 and 2467B, and that's the two here. So this will be the subject of another video. These things are so heavy. So this one here, we're going to do basically the usual capacitor replacements, the reefer capacitors that tend to burn up on the power input. Those little the film caps, the metallized polypropylene or whatever they are, the things that cause problems in all the old gear. Also, there's a bunch of capacitors and even a few resistors that are known to be needing some attention in these units, especially in the power supply. They tend to dry out and cause a few problems. The other thing we're going to be doing is replacing the battery for the RAM. The calibration constants in these units, similar to a lot of old HP of about the same vintage, hold their calibration constants in battery-backed RAM, not in like any ROM or anything, or they didn't have flash RAM or anything like a non-volatile RAM back in the day. So there's a 3.7 volt lithium battery in here, which after 10 or 15 or 20 years, tends to go flat, and that you lose recalibration, and then you can't use the unit. When you turn it on, it just shows question marks on the screen. It doesn't actually boot up or anything. So I guess the next step is let's just turn it on, just to make sure it's going to fire up before we go start replacing capacitors and stuff, and then finally got to fix something anyway. So I don't want to spend all the time restoring it without knowing if there's any problems. So we'll hit the button there. This was actually sold as non-working. The seller said in the listing that it turns on but nothing displays on the screen and it doesn't do anything. And I've seen that a couple times now where people don't realize that these things actually go through a extended boot up sequence. You might see lights flashing here and there, and you might be able to hear on the microphone a few clicks of relays, but they do take a little while to turn on, whereas normal analog scopes, they tend to turn on rather quick, and you see a trace. See, now we've got the trace. It's taken that whole time to turn on. So the seller, not knowing how long these things take to turn on, has gone, oh, it's not working, and they sold it as such. So I got it for a very, very good price, and no one else bid on the thing too. So yeah, it was a bit of a win for me. So we get a nice display there. It's nice and crisp, looking pretty good. We can turn the intensity up and down. I'm not going to turn it up for too bright for too long, but just enough is what you want to set it to. So I think you can see that on the screen there. And we've got the markers. Where do you change the markers? There's some, yeah, you've got the dials for the markers. These dials are a little bit crunchy. They're going to need some deoxit and whatever. But yeah, this has got the option to put those markers on the screen, and it's also got an option for probe power on the back. There's little are they called Nemo or something? I don't know. Some little plugs on the back that you can plug your probe power in to use powered probes and whatnot. So let's see what we got here. Let's just give it a quick run on the calibration output here. Oh, there we go. That one's working. So yeah, I think winner chicken dinner so far. So let's open it up, see what got inside, have a bit of poke around and see what's going to be done. Alright, once you take the case off, you'll see what I'm seeing here. The front of the unit is that way, CRT is under here, there's a few connectors to undo here, and once you lift this plate up, once you've done all the screws, then there is also a connector just here. If I open it up, you'll see there's a connector on there to undo. That one right there. And then this plate will come up. You may or may not have circuit boards attached here, depending on what options you have installed, but that one can go off to the side for now. And this is what we've got. So we've got the front panel controls here, we've got the main power supply section here, we've got the CRT, there's some CRT stuff here, and then the main control board is right there, and you can see there's a battery, that one with the yellow on it. It's a little square shaped thing. So that's what we've got to be careful about replacing, because the RAM, I think it's that one or that one. One of those two is a RAM. So we've got to replace that without dropping the 3.5 or 3 volts or whatever it is out. But that we'll come to that later. So the first things first, I'm going to have a look at the power supply, because that's where most of the attention is required to get this thing working reliably with those reefer caps, and a bunch of these other capacitors tend to dry out because they're under high stress. So once you've got the power supply section out, you'll be greeted with this view of things. Just be sure before you start poking around inside, you heed this warning. This is the cover that sits on top of here. And yeah, 250 volts primary potential. Make sure it's below 24 volts. You poke your leads through the little holes here when that's mounted. And if that's below 24 volts, you're golden. You're safe to go. But just make sure you do that, because yeah, this will kill you. These two big caps, a lot of energy inside those, so just be careful of that. So have a look around. There's a few capacitors here and there. These ones apparently are ones that are prone to failure. There's two of our reefer capacitors which have to come out straight away, and if we flip it over, we've got a shield here which I'll take that off, and underneath there's a few more bits and pieces. So I'm going to go ahead and replace all the capacitors, because some of them are known to be bad. I don't want to be opening this thing up again. Grab the other smaller screwdriver for there. Nope, even smaller again. And hiding under here, we've got a reefer there, and a reefer there, down inside their little baby one. So there's 4 that have to be replaced no matter what. And there's a few other bits and pieces here now. There's one over here, I believe it's this one, it's 100 microfarad. That has to be 100 microfarad. It's part of a capacitor divider for the 8 volt rail. If you put a different value there, it's not going to have the proper 8 volts, and then your system won't work properly. So I think it's that one that has to be 100 microfarad. These ones over here, these sprugs, these are in like a carrier. So I've got some that are going to be the same diameter and no longer, so we can replace those with new ones that are going to fit inside this plastic holder. And the rest are just the standard capacitor replacements around the place. Here's something to be aware of. These clips that are holding the circuit boards together, you'll find they're a little bit difficult to remove unless you know the trick. You get some point-nose pliers, and if you put them in the side, you'll see there's little tabs inside if you have a look on yours. And if you give them a gentle squeeze, they'll come straight off. You can see I've got them in the little tabs there. And just gently squeeze them, and then they'll pop right off. It's probably a good idea to do the same to put them back on, so you're not going to break those little tabs. Easy as pie. Alright, so I've decided I'm going to have a look at these pots. These are from the underside or the bottom of the CRT. There's a few pots there for things like focus and intensity and scale illumination and that sort of stuff. And they were a bit scratchy, so I've removed the little circuit board, this flat flex circuit board with the pots on it, from the machine. It is a bit of a process to do. You have to actually remove the entire bottom circuit board, which is a big job. So I'm not going to go through the step-by-step process on how to do that. If you're able to do it, then you're able to figure it out yourself, I guess. And it's going to blow out the length of this video if I show every little detail like that. It is a rather delicate job, so I don't suggest you do it unless you know what you're doing. And in that case, you probably know how to do it yourself anyway. So I'll show you how to rebuild these pots anyway, because it is a little bit interesting how to rebuild a pot that doesn't have any way to get inside. Some pots, you'll notice that they have the legs coming out the side, and there's a bit of a gap. You can spray your contact cleaner or deoxy inside, but these ones don't have that. They do, however, have some little tabs. So what I'm going to do, against my better judgment, is open up these little tabs and open the pot, and then get inside to give it a good clean. So I've got my little screwdriver. Just going to lever each one of these open very carefully. Alright, and there we are. So you can see on the, wait for that to focus. You can see on the left there, this one here, we've got the wiper. Is that going to focus or not? And you can see in the middle there's a little like a half moon shape. That's the center contact, and then around the top where the strap or that kind of metal piece, it divides into multiple paths. That's how we get multiple points of contact. In this case, there's 4 points of contact. This gives you more reliable contact. And then on the right there, we've got the carbon trace with the center piece there in the middle, and then the carbon trace around the outside. So we're going to give that a clean. I'll get some a Kim wipe and some isopropyl alcohol. And give that a wipe. This one wasn't too bad. Often you get like a bunch of black stuff on there. So that's nice and clean. I'll fold it up and just give the contacts in there a bit of a clean. And then we've got some deoxit fader, this stuff. I just put it into like a this Hacko. It's like a flux pen, so you can draw your flux on the circuit board. But I put the deoxit in there, so it's like a little paintbrush. Get some deoxit on there in the center, and then around the outside. You can paint it on nice and thin. And this fader stuff is good. It's got the deoxit kind of properties, but it's also got lubricant in there so that the pot stays lubricated and doesn't scratch itself to pieces. And then what I've got to do is orient this correctly, like that, and then close it up. Last one, and we're done. Nice, feels good. So I'll continue with the rest of them, and these pots should be good. And the potentiometer lunacy continues because I'm a madman, I'm out of control. The front panel here has got a whole bunch of pots and some of them are scratchy. So they're going to get the old open up, clean out and put back together treatment too. But you can see these are all plastic. There's no metal tabs to undo, but there is 2 little pins. So I'm going to pull them out, open it up, and when I put it back in, I'm going to use the other 2 holes. Because there's only 2 pins, there's 4 holes. I'm going to put in the other 2 holes so it's all nice and tight again. And that should be good. So the way I'm going to do it, I don't have like a press or anything, but if I put it on here so that the pin is overhanging the edge of my pliers, that's like a little spacer there. I've got a little pin punch, and I can push the pin straight out. Look at that. So do the same on the other side. And it opens up. Look at that. So we can get that a good clean. I'll grab my Kim wipe again. A nice new fresh one and some iso alcohol. Yeah. Good amount of gunk coming off of there. And then I'll carefully just wipe just the wiper itself. You can see there the black stuff coming off. And that needs to get the old deoxit fader treatment. And of course, no forgetting a little bit of silicone grease, because that was in there to start with as well. Just a little bit. And that is all ready to go back together. Make sure that's all seated nice. Yep, that feels good. That one goes in there. Now carefully squeeze that in. And then the other one, take out all the old plastic from in the grooves. And that goes diagonally opposite. Like that. Beautiful, smooth as a baby's bum. That's nice and ready to be put back into action. Alright, so I've got the processor and digital control board here, and we're going to replace the battery. This is actually the older version of the board. There's 2 versions. This is the older one. The newer one has a slightly different layer, and the RAM chip and the battery backup is actually integrated into one chip. It's a double thickness sort of chip, and it sits around about here somewhere. This one doesn't have that. It's got the 2 separate, the battery and the RAM separate. If you have the newer board, I don't actually have one to show. Both of my 2467s, the 2467 and the 2467B, are the old style. But there's a different process to replace that, so you can actually desolder that chip wholesale, stick it in a chip reader, suck all the data out, buy a new chip. You can buy new ones with fresh batteries, from DigiKey or Mouser or whatever. Pump that data back in and solder it down to the board again. Maybe put a socket there if you feel like it, to make it easier to replace in the future. And then you're done. Also on those boards, you have to be aware there's some SMD, surface mount tantalums, which do leak and they can corrode the board quite severely. So you have to replace those. It's a mandatory replacement. And if you're unlucky, you have to repair the board, or if you're really unlucky, maybe replace it. But the old boards don't have the tantalums. They just got a few electrolytics, which I've replaced out of just for good measure, and they have a separate backup battery. So this is the RAM chip here, and this is the lithium thionyl chloride battery, the 3.5 volt battery. So we've got to replace that. So the reason I'm replacing this is it's old. It's the original. It's got the date code is 0289, so it's the second week of 1989. Quite an old battery. It is reading 3.5 volts or so, but I've got the graph here from the data sheet, and the discharge curve is flat,
and then suddenly drops off to 0. There's no like slow decline. It's just 3.5, 3.5, 3.5, nothing. And I don't know how close I am to that cliff's edge. I could be right at the end. I could have, you know, half the capacity left. I got no idea really. And I don't want to take any chances. So I'm going to replace a battery. Then I know I'm good for the next 10, 15 or 20 years or whatever. So yeah, that's what we got to pull out. So we got to figure out how we're going to keep the voltage to our RAM chip while we pull this one out, because as soon as we pull that out, that RAM's going to empty itself, it's going to erase, and we've lost our cal data, our calibration data, and we have to recalibrate the whole unit, and we don't want to do that. We've got to figure out where to apply the 3 volts from these batteries into this circuit, so when we take out this battery, the RAM doesn't erase. So first we better check to make sure that 3 volts is enough for this chip, because this battery here is actually 3.5 volts. So I've got the relevant page from the datasheet for our RAM chip, a Toshiba TC5564APL-15 and TC5564APL-15 right there. So if we have a look down here to the DC recommended operating conditions, I'll zoom in a little bit, and you might already be able to see it there. Data retention supply voltage, right here. Minimum is 2 volts, maximum 5.5. So our 3 volts, I've actually measured these batteries at 3.08 volts. Right in the middle of between 2 and 5.5, so that's going to be perfect. 2 AA's will be fine for a temporary backup power supply for our backup power supply. So we've got to figure out now where we're going to connect. So I've got the schematic and then the board layout here, which is the board layout for our board. I'll leave it zoomed in for now. So here we've got our schematic of the battery circuitry. Here is our battery, and we've got this resistor here, and then this diode 2770 and resistor 2770 10k there. So what we can do is where this resistor and then this diode attached to the circuit board, we can actually solder our wires to our new battery pack, to this one. And then when we remove this battery and replace it with a new one, remove this battery again, and then we should be fine. So I've actually found these 2 components down in the bottom corner on our PCB, right here. So if we solder our battery positive, I'll get a bit of a better pointer here. So our positive goes to the top of this diode, and our negative of our backup battery goes to the top of the resistor there. That's going to be parallel with this battery, so we can remove that and safely put the new one in, and yeah, we'll be fine. So as for the backup battery, because you can actually buy these if you're in America from Mouser, but they don't ship international. So I can't replace it with the exact same type. So I have got a Panasonic from Akihabara. This is a lithium battery as well, and it is a 3 volt BR-2/3A. So I suggest that you use the original one because it just fits straight in without a problem. But if you can't find one of these, any kind of backup lithium thionyl chloride or similar battery, as long as it's above 2 volts and below 5.5, you can plonk that in there. So that's going to sit there in place of this one. Now I'm going to solder onto the back because it's going to just be easier. Positive on the left, negative on the right, and negative towards the edge. So if you flip it over, negative is now on the left. So we've got the 2 little pads here. So we go negative here. Make sure that's secure. And then positive here. Whoop. And that's secure. So now we're ready to desolder our battery. There we go. Battery is out. And we can actually see the traces here of the pinout. So it looks like it actually says positive and negative on there too. Maybe if I zoom in a bit more. So a positive is here, negative is here, and the negative trace actually comes up to the other two at the top here, which is convenient because the battery I've got here is like positive and negative one at each end. So I can put that in. I'm going to use little bits of tin copper wire to go through the pads, the holes, and I can put positive and negative, and that will go straight there like that and connect correctly. Perfect. We still got voltage. Perfect. That is done. That RAM chip should still be good. Fantastic. So that board can now go back in the unit, in the machine. And that will be good for another, I don't know, 15, 20 years. I'll put a little label on there with a label maker saying the date that it's been replaced. And that's one job done. So I had a little bit of a problem. Yeah, while I was desoldering the blue potentiometers, which I showed before, I kind of had to remove this flat flex cable, and I delaminated some of the pads. Basically destroyed this flat flex. Not an easy part to get, and yeah, even if I got another one, it was going to be attached to the pots on another front panel, which makes it expensive, and I have to desolder anyway. So yeah, all is not lost though, because I talked to my good friends at PCBWay, and I said to them, hey, I want to try your flat flex PCB service, and they said sure thing, go ahead. And so I made a design, and I got some new flat flexes. Woohoo! Look at that. So I basically copied the design exactly, and I made a few changes. So this board here, or this flat flex, is only single-sided. There's no pads on this side. They're only on this side. So mine is double-sided. It's got the pads on both sides. And also I've gold-plated all the pads. I've got all the pads all gold-plated there, so they're nice and shiny and gold-plated. And also, I went and made all the traces all rounded. There's a few places where I couldn't, but on this one, they're all like kind of the 45-degree angles. On this one, I've made them all nice and curves and, you know, smooth lines. What that does is that reduces stress rises. If you have a trace where it's a sharp corner, when the PCB flexes, that corner can cause a crack to form. But by using nice smooth curves, there's no corner for a crack to form at all. On here, they've done what's called teardrops on the pads. I don't know if you can see that. Maybe if I turn it over, you might be able to see it easier. But on a bunch of the pads, they got like little like tapers going from the pad to the trace. You might be able to see them. Maybe there. So I've done the same as well. So I got all these little tapers going to the from the pads to the trace, and that is the same thing, because if you have a pad that's like the side of the pad and the trace comes in, well, you can crack, and if it cracks across the trace, it's going to go open circuit and you've lost your circuit board. So by having it taper in from the pad to the trace, there's no sharp corners for that to happen. So I said I got 3 of these. There's 2 of them here. The third one is installed. Oh yeah, look at that, beautiful.
it fit perfectly, and yeah, nice. I'm really happy. I'm happy because it came out real good, and I'm happy because I can get my scope working again. So yeah, like I said, I don't recommend going so deep. I did because I have a I don't know, an obsession or something. I've got a bit of a problem where I just keep diving deeper. So yeah, I managed to fix it, but that was a good chance to try out PCBWay's Flex PCB service, and I have to say I am very happy. And yeah, not a problem at all. So if you need some Flex PCBs made, check out PCBWay. They are a sponsor, but they do make a good product, so 2 enthusiastic thumbs up. Alright, for the fan, if it's electrically okay, it's just a bit noisy, you can often replace the bearings. I've already pulled the sticker off carefully, so I could have a sneaky peek inside, get some new bearings. Mine's a Nidac Beta SL TA300DC, model A31437-16, 12V DC at 0.12 amp. So you can undo the little clip inside, and then pull the thing apart. It's a little bit of a delicate operation. You can pull the thing apart and then replace the bearings and put it all back together. If we can get that, there we go, it clips out, and then it's a washer, so I'll keep these in order. That pulls out, we've got one bearing there, and we've got the other bearing with a spring in between there. Okay, I've got the new bearings here. They're a 693ZZ. The ZZ just means it's got a metal seal on each side. If it was RS or 2RS means 2 rubber seals. So they're a 8mm outer diameter, 3mm inner diameter, and 4mm thickness. So we stick the bearing there, then the spring, and that can go in there, like that. Bearing in the back there. Stick that washer on, and then the little clip. I used to use a 3mm-ish little nut driver, and there we go. Beautiful. So I'll just give that little clip a squeeze just to make sure it's nice and tight. Yep. And finally, we can put the label back on. And that is all done. So that is a 12V. So I have got 12 volts up here. Let's see what happens. Nice. Holding up to the mic. No weird noises. Perfect. That's rebuilt. Don't have to buy a new one. Fantastic. Alright, so it's all back together, minus the case, and ready to turn on and see if it works. I did do a sneaky power on just to see if the voltage were correct, and they were absolutely spot on. There's a test connector on the bottom board where you can test all the different voltages, and yeah, they're perfect, which is fantastic. So at least something's going right. So as a quick overview of what we've done, we've replaced the reefer capacitors in the main board there. They're all a bit starting to crack and whatnot, so they're all being replaced with I believe Kemet brand of the same ratings and the same values and stuff. Replaced all of the electrolytic capacitors everywhere. We have got new flat flex down in behind the front panel there. Cleaned out all those pots. If we turn it up, we have got a couple new capacitors and the new backup battery installed. On the underside, we have got new capacitors in the entire board. That power connector, or the voltage test connector, is just here. Like I said, testing okay. I put a heatsink on this chip here, the U500, I believe. I think it's vertical control chip or something. I won't go into detail on that one in this video. It's a bit of a debate whether that's required or not. I figured, it's not going to hurt if I stick one on. But the video's getting a bit long, so I do have that other scope to look at. So we'll look into this one in a bit more detail in that video. Nothing else has really changed on here except I cleaned the beam find switch, rebuilt these pots for the CRT controls, and also in this side here, a few new capacitors in there. Also, of course, we've got the rebuilt fan, and the front panel has been all cleaned. So it's all nice and shiny and clean again. So let's stick this case on, hook it up, and see if it works. Alright, we've got it set up here on the bench. We've got it sitting on top of a TM500 series 4-bay mainframe, and we've got a few modules plugged in. Some of these modules and stuff I've done previous videos on. Some I have to make videos on once I get to restoring them and repairing them. But yeah, you can look back in the history and see those videos that are there. So the first one here, we've got a TG501A time mark generator. Then we've got a PG502 pulse generator and an SG504 leveled sine wave generator. So we'll turn this thing on. It does take a little bit to turn on. It does a whole build up sequence, flashes lights and clicks relays. So you can see on the display there, we're getting the pulses from our time mark generator. I've got the time mark generator set to 10 nanoseconds. And this here, the seconds per division, the range there is set to 5 nanoseconds per division. We're getting one pulse every 2 divisions, so 2 divisions times 5 nanoseconds equals 10 nanoseconds. So that's reading correct. Fantastic. All right, let's go to channel 2. And we're working on the pulse generator now. And I've got that set to the period to 10 nanoseconds and the pulse duration to 5 nanoseconds. And you can see the period down the bottom there between the two is 2 divisions, and then at the top it's the pulse width is 1 division, so that's 10 and 5, so that's also fine. Fantastic. So we'll go to channel 3, and this is the leveled sine wave generator. So this is putting in a leveled amplitude no matter what the frequency is set. At the moment I've got it set to 400 megahertz, and if you watch, if I turn this up, watch what happens to the amplitude. It drops. That's because we've gone above the frequency rating of the scope, so our amplitude drops because we've gone beyond what it can handle. And that's perfectly normal. If we head back down to 400 megahertz there, that's right on 400 megahertz. Now if I turn it down, you'll see it stays the same amplitude. It doesn't shrink or grow. That's perfectly fine. That means we're reading correctly. Bring it back up to 400 megahertz right there, and we're looking pretty good. So let's head over to channel 4 and see what that says at 400 megahertz. Looking alright. It's a little bit taller. I might have to do a little bit of a tweak on that channel 4 maybe, but that's looking alright. If we bring it down in frequency, it's dropped down to the same level as channel 3, but if I come up to 400 megahertz, it grows just slightly, just at 400 megahertz there. So that might need a little bit of a tweak. Not like I'm going to use channel 4 very often anyway, but yeah. And then as we go above 400 megahertz, it drops down as shown previously. So a little bit of compensation there somewhere, maybe a dial or something inside to tweak, but that otherwise is working fine. Fantastic. All 4 channels work. We're getting all the signals as we expect, and yeah, it's good to go. So I'm going to say that for now is done. Thumbs up for me for getting that done without blowing the thing up, except for that one little hiccup with the flat flex cable. So special thanks to PCBWay, 2 enthusiastic thumbs up for them for supplying that new flat flex cable. And yeah, thumbs up for the working scope. So if you found that interesting or somewhat informative, hit that like and subscribe. We're going to have a lot more videos coming for you in the future, and we'll see you in the next one.